Alrighty, howdy everyone. Welcome to another Wednesday. How are we doing today? Good, great. Are we all excited for break next week? Yes. I guess in terms of like business, in terms of class, if you're in Dr. Altamos's class, your quiz was due yesterday. If you're in Dr. Altman's class, then your quiz is due tonight by 11:59. So just make sure that you take that on Canvas. And then exam 2, I think, is the first week in April, if I'm correct. So there's a couple weeks after spring break, and then you're taking another exam, and then the semester is almost over. So almost halfway. Almost, like, I think you might be halfway. After spring break, you're definitely halfway. All right, any questions for me before we get started in terms of like administrative stuff? Okay. So I guess this hour is yours. What questions do we have about our material so far? Our material from last week. Yeah.
Can you go over again how the N, L, M, L, and MS, like how you find how to like interact with those?
Are in those, yeah, absolutely. So if we're doing quantum numbers, we know that we're given N, L, M sub L, and N sub S. So when we have N, what does N tell us in our quantum numbers? Yep, that's going to tell us our energy level. And what are some examples of energy levels that we can have? Yep, 3. What else? 1, right? 2, 4, 7, 6, right? All that fun stuff. Right, these just have to be whole numbers starting from 1. Your first energy level is going to contain hydrogen and helium. And then your second energy level is going to start with lithium, and it just goes across your periods, right? So every period that you have on the periodic table, 1, 2, 3, 4, 5, is going to associate with the letter N. Okay. If we have L, what is the rule for L?
N-1.
It's N-1. Good. So this is N-1. And what does this tell us? This is our subshell. Good. Right. So if we have N is equal to 1, what can L be equal to? L is only equal to 0. And if L is equal to 0, what does that correlate to?
S.
Good, right? When L is equal to 0, yes, L equals 0. Yes. Right, and that's for every single energy level. So even in energy level 4, if your L is 0, that still means that you're in the S subshell. You're just in the 4th energy level of the S subshell. Okay, what are our other L values? 1, 2, and 3. Those are the ones we care about. What is L, or when L is equal to 1, what is that letter? That's P. What about 2? D. What about 3? Good. We all know where we can find those on the periodic table. Yes, we all saw that in terms of the S block, the P block, the D block, and the F block. Yes. If you don't, happy to explain. You don't know where it is, or we do? You do? Okay, great. Okay, so your L is going to be equal to your subshell. Your M sub L is going to be equal to what? What does that correlate to? Yep, good. That's your orbital. Right, and this has to deal with the orientation around your nucleus, or around the coordinate diagram. What is your rule for M sub L?
-L.
Good. So this has to be negative L to L, and that's including 0, right? And all of your integers. So if L is equal to 3, then we can have -3, -2, -1, 0, 1, 2, and 3 as our options. Right, this is where your electrons come into play. Because in every orbital, how many electrons can we have? We can have 2, and that's indicated by M sub S, where M sub S is your spin, and it can only be +1/2 and -1/2. So in each of your orbitals that you have, right, if we're in the -3 orbital, that means that we can only have 2 electrons in that -3 orbital, and those are going to be +1/2 and -1/2. Right, so they have opposite spins. So in your F subshell, how many orbitals do we have in our F subshell? We have 7. So how many electrons are in our F subshell? We have 14 total electrons. Okay, does that make sense how we get it for just F in general? Okay, but if I say that we're in the 3rd energy level, how many orbitals are in the 3rd energy level? Where'd you get 9 from?
So, we got like, so for the S, we will have 1,
Mhm.
and then for P we'll have 3 orbitals, and then for D we have 5. So
Beautiful, awesome, right? So if we're in the 3rd energy level, we have to look at what our options for L is, right? I'm asking for how many orbitals. It has to go down in your quantum numbers letters, I guess. Right, so if we're in N is equal to 3, that means that L can be equal to 0, 1, or 2. So that means we have the S, the P, and the D, F subshell, or the S, P, and D subshells. And so that means that our L values can be -2, -1, 0, 1, 2. But that also, I'm sorry, this is M sub L. Can be -2, -1, 0, 1, and 2. But that's when L is equal to 2. But also M sub L can equal -1, 0, and 1 when L is equal to 1. And M sub L can also equal 0 when L is equal to 0. So if we have these different options for M sub L, how many total orbitals are there? Right? We have 5 when it's equal to the D subshell. We have 3 when it's equal to the P subshell. And we have 0 when it's equal to, or sorry, we have 1 when it's equal to the S subshell. So 5 plus 3 plus 1 is going to be 9. So we have 9 total orbitals. So how many total electrons are there in the third energy level?
18.
There's 18 total electrons. Does that make sense how we found? Yeah, go ahead. Yep. So, right, we have 9 different orbitals in our third energy level, right? We see that from the M sub L version. Each of those orbitals can hold 2 electrons. So we just took 9 times 2. Yes.
So we have
I believe that works because if we have N is equal to 2, then we'll have L is equal to 0, 1, and M sub L is 0, 1, 0. I think that works. Yes. Yes. Yep. I think that's correct. Say that again. If they're just saying how many orbitals in the N subshell, like whatever value that is, then that formula works. But if you're given like how many orbitals when it's the fourth energy level and the third, right, or L is equal to 3, right, then you have to do a little bit different math because then you narrow down how many orbitals you're looking at. Does that make sense in terms of your question?
So the electrons come from all of the possibilities of L?
Yes. Yep. Right. So we can get more specific. We can say, how many electrons are there in the D subshell at the fifth energy level? All right, so now I'm asking how many electrons are there in the D subshell of the 5th energy level? Why you get 10?
because I mean, D subshell will have 5 orbitals, and automatically a subshell has 2 electrons in an orbital, so that makes it 10.
Awesome, right? Your D subshell will always have 10 electrons. Right, if we go back to our quantum numbers, if we're in the D subshell, that means that L has to equal 2. And if L is equal to 2, then that means M sub L can be -2, -1, 0, 1, 2, which means we have 5 orbitals times 2 equals 10 electrons.
How do we know those 2?
Because I told you that we were in the D subshell. Yep. Also, if we look at the periodic table, right, we're looking at that red portion in the center of our periodic table. That red portion has 10 elements in it. How does our periodic table get built up? What are we adding? Protons. And if we're at neutral, if the protons are the same, what's the same as protons in that case? Electrons, right? So for every element we have, we're adding a proton, but we're also adding an electron. And so for that D block in the center, there's always going to be those 10 elements. And so there's always going to be 10 electrons that can be in your D subshell. Okay. So you can also use this too to count like the third energy level that we talked about. We know that we have, right, 1s across the top, then we have 2s, 2p, 3s, 3p. You can count the 3s on the 2 on that side. That's going to be 2. We have the 6 in our 3p, and then we have the 10 in our 3D subshell. So 2 plus 6 plus 10 is going to be 18 total electrons, right? And that matches the question that we talked about earlier in terms of how many electrons are in the third subshell or the third energy level. Does that help find electrons throughout? Does that help you? Okay. Great question. Any other questions about quantum numbers, finding electrons? Does that visually using the periodic table help a bit too? Does everyone? Alrighty, what other questions do we have?
The B subshell thing that we got the 2 from, is that basically the same thing as like if it was S, then it would be 0? And
Yes, yep, exactly.
E is 1.
P is 1, yep. And then F is always going to be 3.
F is 3?
Mhm.
So then that's S.
Yes, yep, 2 total electrons. What other questions do we have? So, go ahead.
I was gonna say that, I know it's kind of going back, but do you think we can go over some chapter 5 things, talking about like gas law equations?
Yeah, absolutely. Is there anything specific from that?
Maybe just the second main thing.
Like just PV equals nRT kind of stuff? Yeah, absolutely. Yep, and what was your question?
I was gonna ask you to go over the patterns.
Yeah, absolutely. We'll do gas laws, then we'll come back to this. Okay, so when we do chapter 5, this is all about our gas laws. So what is our big gas law that we use? What's our ideal gas law? PV equals nRT. Okay. If we're to label PV is equal to nRT, what is P here? This is pressure. What's the unit we usually use? Good. What's V? Volume. What's the unit here? Good. What's N? Moles. Mole. What is T? Temperature in Kelvin. And then what is R? Universal gas constant. What is it? Yep. Anyone know the units?
The moles times the Kelvin.
Close. Gonna be liters times ATM over mole Kelvin. This is given to you. You don't need to memorize that, but you might use it enough for you to learn it. Important to note for your universal gas constant is that, right, those units do match your other units in Pivnert, right? It has the liters, ATM, moles, and Kelvin. If you're using the 8.314, that one's in joules as an energy unit. So if you're talking about like binding energy or energy of an electron, that's when you use the 8.314. In this case, we're using the 0.08 because we're in gas laws. Okay, so that both of those will be given to you on a formula sheet. Alrighty, I think the big thing with Pivnert is just knowing that temperature has to be in Kelvin. If you're given Celsius, which you usually are, you must convert that to Kelvin or else your math will be wrong. And then like pressure as ATM, I think is the most important, is another important component. So if we just do a practice problem.
figure out, get that answer, just from your kind of thing. Would you get, I'm gonna send this to. Oh, yeah.
Alrighty. So for this question, we have a sample of argon gas at STP occupies 56.2 liters. How many moles of argon and the mass of argon are in this sample? Do y'all want to try this on your own? Yeah, okay. Give you a couple minutes to get started. Does everyone know standard temperature and pressure conditions? What are they? 1 atm.
Is it 0 degrees Celsius or is it 1 degree?
I believe in this case, it's 25 degrees Celsius. There is a case where STP becomes 0, but we'll call this 25 for now. I think there's a case where STP is 0, but I think for gas laws, it's 25. I'm not mistaken. Okay, like STP is 0, but we're gonna do 25. Okay, STP at 25 comes later in the semester. Right now it's 0, but we're gonna pretend STP right now is 25 degrees Celsius, just for the sake of the question. What's that? I don't know, I haven't done it yet. What'd you say? 2.3? That's what I got. And then the mass. Where's P table? Say that your question again.
Don't we just divide the 56 or the, yeah, 56.2.
Close. Close. So when we get moles equal to 2.30, right? This is in mole. What's our unit on our periodic table?
Oh, I just realized. We use PVNR too. Right?
Yes. Yep.
Okay, I was just doing the 1 mole equals 22.4 meters.
Yes. You could also do it that way, because it is a STP. But I told you STP was 25 and not 0, so it'll be slightly different. Yep.
Yeah, so
Yep.
if the temperature was 0, then we would have been able to.
Then you could do that directly. Yep. Yeah, thank you. Alrighty, so. Right, we got PV is equal to nRT. We know that our pressure is gonna be 1 ATM. Our volume is 56.2 liters. Bless you. And we're looking for our moles. We have 0.08206. And temperature, I told you was 25, but it's actually wrong. It is 0, but for the sake, it's gonna be 298 Kelvin. So if you solve this, depending on, right, multiplication, division, you do you. You end up with 2.297, I believe. So that can go to 2.30 moles of argon. If it's on the quiz, do 0. Yep.
It'll specify.
Yeah, it'll tell you the temperature probably. 25 comes later in the semester. I jumped the gun.
One of them was on the homework question.
At 25, yes. Sometimes they just tell you it's straight up 25. 25 is like room 10, so. Alrighty, so once we're given moles of argon, right, this is our mole portion of this. 2.30 moles, we know that argon from our periodic table is 39.948. This is going to be grams per mole. So in order to get rid of moles, you're going to take 39.948 grams over 1 mole. And I got 91.8 grams of argon. Questions on PV equals nRT? No? Okay. Absolutely. That's what I was going to look up next. Yeah. Mm-hmm.
We're reading it on a code, not looking.
Let's see.
If they group, we'll collaborate. Yeah. No, because I was excited, I was like, yes, I'm not even going to have part one, and those things, and because I had no. That's how much I used to get. I mean, study about part two, study part two. It's the longest one with 12 sections, but.
I had one in my equity class at nine. So I basically just read it.
Yeah, it's always.
And now, like, just
It's standard, it's standard. It's like the whole. It was 8 last time. No, it's 7. It's always.
You'll be given that. What did I do? Another one. Alrighty. So kind of building off of the question we just did, we have 80 liters of oxygen is collected over water at 50 degrees Celsius. The atmospheric pressure in the room is 96 kilopascals. What is the partial pressure of water at that you're collecting? Is this something you want to try on your own? Yeah, okay. If you get stuck, raise your hand and I'll give you a couple hints along the way. Right, remember we're doing partial pressure.
Partial pressure has a specific formula, but it's like, P initial divided by P total.
Close.
Then there's a number like that. I remember, and that's not what's pressure, but I use it
So-
for more to the-
So what's P initial or P1 over PT is equal to, yep. What is that called?
No idea.
What does that tell you?
There's just gonna be oxygen plus water.
So if I give you this,
And then the other one is N1 divided by N.
so what does that give you? This is mole fraction, yep.
Yeah, so that's what I did. Like, whenever I get stuck on the question, on all one.
What is partial pressure? So what does partial pressure mean? Parts of the whole, right? So if we have the whole is going to be P total. What are the two parts of this question? The pressure of pressure of oxygen and pressure of water. Do we know the pressure of oxygen?
Yeah, but I don't remember.
Yes, so- Right, we're looking for this. Right, we're looking for what is the, sorry, not the part, sorry, we're looking for water. We're looking for this. Yes. Yep, so we're given our pressure, what's our pressure total? 96. How do we find the pressure of oxygen?
Well, we can see the 96, kilopascal, you just convert it into ATM.
We can do Pivnert, yep, right, so we know that we're given 80 liters, right, is our volume. We can assume that we have 1 mole. We are given R, and we know our temperature is 50 degrees Celsius. Right, so we can say pressure is what we're looking for here.
Because it's the atmospheric pressure for the entire. So which one is on right? And then so the first we find and then from there we get because we need to subtract the total from the whole.
Yes.
What is it?
Because you're not given any other information, so you can just assume 1 mole. I'm also kind of coming up with this on the fly, so they'll give you more information too. You said, yes. You would for this one because your R, like, so in Pivnert over here, right, your R is gonna be in liters, times ATM. So you want to find your pressure in ATM, and then you have to convert, so you have to convert your kilopascals, ATM to kilopascals. Oh, yes, it should be converted. This is 96 kilopascals. Right, so it should be converted to one or the other. You can find your pressure in ATM and then convert it to kilopascals, or you can take your kilopascals and convert it to ATM. doesn't matter. You don't need the funky X for this one.
You don't?
Mm-mm. Nope, because we're not asking for mole fraction or, we're not asking for mole fraction and we're not asking for part of the whole in terms of, like a value. That's just a separate thing, right? That you have two different ways you can use partial pressure. The one of Dalton's partial pressure where the sum of the parts is equal to the whole. Or you have mole fraction where it's the partial pressure of the gas is related to the number of moles of the gas in the system.
What is the quiz open?
When does,
Like,
probably Friday, right? Because you're in Altamosas, yeah, Friday is usually opened up by.
Cause that's weird. That's it. So this function is easier to function. If you lose media, it doesn't. No, it's just a matter of like how much we apply. So, 0.08, 0.06, right? Which one? It's, yeah, you can either do that or you can do 0.0821. Either one. Just 2 nines or something per factor. So most likely all this has to be either rounded up to 3 decimal places or 2 decimal places, it's not more than that. If you need more, then you use the tool set.
Alright, so to kind of go over this one, right, we're gonna use Pivner to find the pressure of our water. And so we have a pressure of 33.571 ATM after we just use Pivner directly. I'm sorry, after we converted it from ATM to kilopascals. I converted it that way just so, I don't know, I was using it. And I don't have to convert the 96. But we know that 96 is our total, so then we're looking for the pressure of our water. That's what our question is asking for. So we get the pressure of the oxygen is going to be 33, and the pressure of our water is going to be 62 after we subtract that from the total.
So you just assume that there's no mole.
Yeah, because I'm kind of making this up on my own. I sometimes forget things. But you can assume 1 mole if you're not given any other information. But they would usually tell you how many moles of something there is, or they would make you find it. Yeah. Does that help with partial pressure a little bit? Okay. We could do, is there any questions on this one before we move on? A little complicated using both of them.
Is the watch book?
Mhm.
Watch the recording. It wouldn't like there today. I've already taken a look. That's true. I should watch it like the day. I'm gonna see how badly I messed up.
Alrighty, so for this question, we have 3.125 moles of oxygen, 0.125 moles of water, and 2.175 moles of nitrogen are combined in a container. What is the partial pressure of each gas and the total pressure of the container? So this is where the funky X comes into play. Yep. So right, we know that the funky X is coming into play because we know that we're looking for mole fraction of things, right? We know that the mole fraction of, we'll call it oxygen, the mole fraction of water, and the mole fraction of N2 is going to be equal to the mole, right? The moles of oxygen over the total moles, the moles of water over the total moles, and the moles of nitrogen over the total moles. Mole fraction is directly related to partial pressure, where the pressure of oxygen is going to be related to the total pressure. Yeah, it doesn't really matter too much about like temperature or pressure, or sorry, temperature or volume here. We just know that this all is happening in a container. Alrighty, so how can we go about finding the partial pressure of each of these, or maybe even the total pressure of all of these? Right, so we can do, right, mole fraction in terms of, we'll say oxygen first. We're looking at mole fraction of oxygen. What do we know? We have 3.125 moles.
Mole fraction based on the equation. And then we know that we use
Because we are given moles and we're asked for partial pressure and total pressure. We know that mole fraction is the part over the whole. That's directly related to the total pressures of everything as well. What's our total moles here?
Yeah.
Okay. Does this give us? What value should this give us? Yes, right. So we have a decimal that we're working with. Right, so the mole fraction for oxygen is 0.576. How does that help us with total pressure or partial pressure? That's the percentage that oxygen makes up. But do we know what our total pressure is to find a percentage yet? How can we get that? Yep, so how can we get total pressure if we're just given the moles of something? Yeah, it can come from total moles, right? So, right, total pressure is equal to total moles. In terms of, like, they're not equals, I guess they're correlated. What's the thing? Correlated. They're correlated. They're related, right? They're both on the bottom half of that fraction. So we can use PV is equal to nRT. We're going to, I think I should say that I think I need to give you that total volume. of container is, someone give me a number. 15? 15, well, we'll say 1.5 liters. Okay. So if we're given that our container is 1.5 liters, we can now say that our pressure, our PT, times 1.5 liters is equal to our total moles, which is 5.425, 0.08206, and then write STP, we would say 273. So now we can get that our total pressure is a number. So our total pressure is 81.02 ATM. Does everyone see why that is and why we can use? It is a lot of pressure. Again, making it up on the fly. All right, does everyone see how we found total pressure based off the total moles? Right. So now we know that this value, 0.576, is the percentage of oxygen that makes up this pressure. So now we can say that 0.576 is equal to the pressure of oxygen over our total pressure. So the pressure of oxygen is 46.7 ATM. We found that with our mole fraction. So in the top corner up at the top. Yep. We did that first. Yes. Yeah, it would tell you STP. If they don't tell you temperature, you can probably assume STP, which is going to be 0 for gases, or 0 degrees Celsius for gases. Yep. But they actually made a quiz, so they should have all the information given to you in the question. Okay, does that make sense how we found the partial pressure for oxygen? Okay, so how can we find the partial pressure for H2O? We would do the same thing, but now we already have our total pressure. So now we can say we have 0.125 moles of water over 5.425 moles total. We don't even need to find that funky X anymore, right? We can just say that our pressure of water is divided by 81.02 ATM, and we can solve for a ratio directly there. Yep, sorry. Does that make sense how we set that up, right? We're not finding that in between step anymore. We can just directly solve for the pressure of water because we already have total pressure. So I got pressure of water is 1.87. And how would we find our pressure of nitrogen? We can find it the exact same way. What else can you do? You can subtract, right? You can say we have 81.02 minus 46.7 plus 1.87. That would give you your pressure of nitrogen. Right, and you can check it right by doing the one that you didn't do. You can go back and use the fraction and see if you get 32.5 ATM. What questions do we have? Does that make sense? Pressures, yes. Okay, great. And then we'll do one last density. Okay. So for this one, we have what density will aluminum chloride vapor have at 225 degrees Celsius and 0.939 ATM? We consume, our volume is 1 liter. Do you want to try it or talk through it? Eventually you'll have to. Density is going to be mass over volume. I can tell you aluminum.
So whatever your max is. For this one, what it is, you PVR to figure out the number of models, convert it to grams. And technically, since volume is just one, it just be that grams over liter. Just convert it.
Yep. Right, so essentially for this one, you know that your volume is 1. So you can solve PV equal to nRT. For, I guess you can do N over V. Because that would be moles over volume, right, instead of mass over volume, but it's pretty close. Is equal to P over RT. In this case, right, volume is 1, so that just cancels out. So, but you still have your units, right? So you have N over V is equal to your pressure, which is 0.939. R is 0.08206. And temperature is 225 plus 273. So N you get to be
Moles of volume, say, you know, you can convert the moles into, grams.
Mhm.
So, and over base basically,
It would say
but in
more,
different units.
or it'd be N, because N is one.
Right, we're given N over V is moles over this many moles over liters. And we know that we can convert moles over liter to grams over liters if we use our molar mass of aluminum chloride. Okay, so we need to take 0.02298 moles over liters. It's going to be 1 mole is equal to 133, I believe. Yeah, 133.34 grams-ish. So your density will be equal to 3.06 grams over liters.
There you go.
Does that make sense that we would solve density for this one?
So. 5 plus 773, that is 270.
273, yeah, 225 plus 273.
Oh,
Sorry, we're just converting to Kelvin. I just didn't plug it into my calculator. Does that help my partial pressure people and gas laws? Yeah.
Density in a way, it's kind of like molarity, moles over liters.
It's, they're related. They're related, but they're not the same. Because it's very much, in this one, in this case, we have only 1 liter of something, so they're a little bit more related. You could have different volumes, and then that kind of makes it different as well. Yep, yep, but they're related. Yep. Yeah, yep.
Adding molar mass of, aluminum. Right. Yeah, you want to figure out.
Yeah, they just sit out in.
But generally, they don't really ask you.
What other questions do we have on density and gas laws? Chapter 5. Feel good? Feel better? Yeah. Okay, great. Okay. And then you wanted periodic trends, like what we talked about in class today? Okay. So if you're in Dr. Altman's class, I don't think you got this far. But we'll quickly go through the periodic trends. So periodic trends is all based off of your effective nuclear charge. And basically this is going to be the balance between core and valence electrons. So does anyone know what happens to size as you go down the periodic table? Yes. So size increases down periodic table. What happens as you go across? So you're going from metal all the way across to non-metal. It gets smaller. Yep. Size goes down as you go left to right across the periodic table. Right? And why does this happen? As we're going down, right, as we go from lithium to sodium to potassium, we're given what period is lithium in? Hydrogen's in 1. What's lithium in? 2, right? Periods is going across. So lithium's in 2, sodium's in 3, potassium is in 4. So for hydrogen, we're just given the nucleus. Thank you. And then we have one core electron. But as we go to lithium, we now have our first subshell, and then we have a whole nother second subshell. As we go to sodium, we now have 3. As we go to potassium, see a bug. We now have 4, right? We can see that those core electrons keep on expanding as we go down the periodic table. As we go across, however, across as in left to right, like you're reading it, we're only just adding electrons to our shell. So we're given in the second period, we have the 2 in the center from our 1s, and we're given 1. Right, and now we have 2. Now we have 3, right? And we're just going to keep on adding that to our outside shell. We're just going to keep on adding more electrons to that shell until we get to our noble gas. But as we're adding electrons, what else are we adding? We're also adding protons, right? So the more that we're adding electrons, what is happening to the charge at our nucleus? It's increasing, right? We go from, if we're in the second period, this is 3 plus 3 plus 4 plus 5, right? So now we have more pull on those electrons on the outside to our nucleus. If we think about the lattice energy, Q1, Q2, right, this one, that charge is increasing. So the pull and that energy that we have is increasing as well. If you think about it, I always relate this to like camp counselors, right? So if you have 5 adults in the center looking after 5 children, those are going to have a tighter pull than maybe 3 adults on 3 children, right? Because there's less adults to keep after all of the kids. Okay. No, it depends on if you're going across or down, right? Because if you have more electrons going across the periodic table, they're all going to be added to the same shell. So it's going to tighten it up a little bit because now you have more charge pulling them and more attraction pulling them all together. Okay. But as you go down, right, you're adding more and more layers to it. So that's why it's making it bigger. Okay. So that's size going down and across periodic table. And when I say across, it's always going to be left to right. Okay, what other trends? If we have, what else did we talk about today? I can't even remember. That's really the big one. Ionization energy. Right, we say in general, as we go down periodic table, what happens to ionization energy? So is our electron more or less tightly held as we go down? It's less. So do you think it's going to be easier or harder?
No, it will be easier.
It'll be easier, right? So again, if we think about camp counselors, right? You have one counselor at the center keeping an eye on a kid that's really, really far away. Or you have one eye on a counselor, or you have a counselor keeping an eye on a kid that's right in front of you. Which one's going to have an easier time escaping from camp? The kid really far away, right? So that really, really far away electron is going to have an easier time getting out of there than one that's like right in front of you, right? So that's why it's harder to remove the core electrons as compared to the valence electrons. Okay. Same thing. If now we have your smaller, right, kid's really, really far away, but now they're a little bit closer to the camp counselor. Are they going to be easier or harder to get rid of? They're going to be harder, right? So your elements that are now like fluorine or chlorine, right? You have more kids on the outside, but they're all brought in a little bit closer together. These are going to have a really, really hard time removing those electrons. So as you go across the periodic table, ionization energy is going to go up generally. Right? Because now they're smaller, they're closer to the nucleus, they have more attraction on them, it's going to be harder to pull them off. Electron affinity, so this is ability to remove an electron. electron affinity is, I call it the want for an electron. Or, I guess that's more electronegativity, but electronegativity affinity is kind of similar, related. So as you go down a periodic table, do those elements want an extra electron, or they want to get rid of that electron? In general. Right, a really, really big atom, does it want to add another electron to it? It does depend. But let's talk about like francium is in your bottom left corner.
Thank you.
Thank you. Right, it only has one electron in its valence shell, and it's the biggest atom on our periodic table. Do you think that one wants an electron? No, probably not. So that electron affinity is going to be really, really small. It doesn't want it. So as you go down, your electron affinity will also go down. As you go across a periodic table, right, if we think about fluorine, that's a really, really small atom that's only one electron away from being like a noble gas. Do we think that wants an electron or not? It does. So do we think going across, what happens to our electron affinity? It also goes up. Okay, so those two trends are the same, but they just mean slightly different things. Yes. Mm-hmm.
But it's easier to remove electrons from the atoms that want electrons.
Thank you. No. So the is right, it's your ability to remove an electron. So if we have fluorine, right? This has 1, 2, 3, 4, 5, 6, 7. Right? This electron here is going to be really, really hard to remove because it really wants another electron here. So its want for an electron, right, this portion down here, is really, really high. And so in order to remove that electron, it's going to take a lot of energy because it's so tightly held. Does that make sense?
Yeah.
Right. So it's the ability to remove an electron is high, and the ability to put an electron on is really high too. Right? Because they're talking about opposite things that mean the same thing. Or that are related to mean the same thing. Does that make sense? Does that help a little bit? Okay. And then the last thing we talked about was ions, right? So we talked about sodium. Sodium has how many electrons? Does anyone? Has 11. 11 protons. Yep, thank you. So neutral sodium has 11 protons, 11 electrons. Does sodium make a cation or an anion? Cation. Yep. So it goes to sodium plus. How many protons does sodium plus have? It has 11. How many electrons does it have? It has 10. So what happens to the size? Right, so let's draw it out. We have 2 in our center. We have the 8 of our core, and then it has 1 valence electron. So if we remove this valence electron, what does it do? It gets smaller, right? We're removing that outer shell. Yes. Yep. Well, any anion or any cation will get smaller. Okay. We're removing that outer shell. So now it has 8 as its total and it's in its shell. Does anyone know what element comes right before it? So neon has how many protons? 10. How many electrons? 10. So it also looks like like this. Does that mean that sodium plus and neon are going to be the same size? No, but not for that reason. Nope, but not for that reason. Nope. So sodium plus has how many protons and how many electrons? Is that the same or different? They have different. What about neon? Are they the same or different? They're the same, right? So let's think about it like camp counselors. We have 11 counselors looking after 10 kids. Are they going to stay close or are they going to stay far? Closer, right? Because we have more counselors in comparison to kids, right? So we can have, it's like holding, it's like if each person walking a dog has one dog. And then there's an extra person that can go around and help everyone else with it out. It has a leash tied to all 10 of them, right? Neon, it's one dog and one walker, right? Sodium has a dog per walker and then an extra person. So those dogs can now be held out and held tighter. So because we have more protons than electrons, we can now pull them even closer to each other. So sodium plus is smaller than neon.
So higher proton to electron ratio means it's item is small.
Smaller, right? Because we have more attraction, we have more positive charges pulling in on those electrons, on those negative charges. Okay, but then we have fluorine. Fluorine has 9 protons and 9 electrons. Fluorine minus has how many protons?
And then it's a thing.
And then we have 10 electrons. So this too now looks like this. What is fluorine minus going to do compared to good, right? Now we have more electrons than protons. Now it's like having a dog on no leash, right? But we have 9 walkers, but 10 dogs, right? So now we got to do double duty on some of them,
I feel like more than 10 run away.
right? We have more things trying to run away, but less things holding it together, right? So now it can spread out a little bit, right? Thank you. Right, so if you're a camp counselor, right, you got nine counselors, but 10 kids, one kid's going to run away. They're going to spread out a little bit more because you can't have all eyes on them at one time, right? We don't have a buddy system here. So is fluorine minus going to be bigger or smaller than neon? It's going to be bigger, right? Fluorine minus is bigger than neon. So if we're ranking size, we have sodium plus, and then neon, and then fluorine minus. But for ranking size, not ions, we have fluorine, then neon, then sodium. Actually, I guess in terms of trends.
Without the charges, it just goes from like number of protons.
Yep. This goes your normal periodic trends.
And then so just. Wait, okay, so then why, oh, okay. Okay.
Yes.
That's the first part of that.
Yes.
Would be
Next quiz will have like periodic trends on it. Yep. And then in chapter 7. Yep. Yes.
The key part of the ground table of public, I know it's one less, but I know there's a few sections in there.
Yes. Yep. So
And then like anything with the gas.
yep. So in your D block, this right, you have, this is 4 in the corner. Your D block will always be 1 minus whatever period it's in. So this Scandinavium or Scandium starts the 3D. Yttrium starts the 4D. And then hafnium, I don't think I've ever used that element in my life, is the 5D. And then Rutherfordium is your 6D. Right, so it's always going to be 1 minus. In terms of exceptions with your noble gases, it's your chromium, I think no, not chromium. 4D, 1, 2, 3, 4, 5, 4. Yes, it's chromium. It's the chromium one. Your chromium is going to have the exemption because that would be the noble gas right before it, argon. 4s2, chromium would be 3d4. But in 3d4, if we have 4s2, 3d4, it looks like this. This now makes you have an orbital that has nothing paired, but then a 4s that has something paired. So it's easier and more energetically favored to bump this paired electron up here. So it actually looks like that, right? And that happens for everything in the chromium category here. And that also happens in your copper category as well. So chromium, molybdenum, tungsten, and seaborgium. Borium is for Bohr though. Bohr model. Ooh, 107. I think there's a couple fun ones down here in the D block. Or the F block. Promethium, like hello. Yep. Right, there's nobelium. Nobelium is 102. We had someone give a seminar and he's like expanding the periodic table of like trying to build like higher elements, right? Because it's just putting neutrons and protons and stuff. And we're like, what would you name your element? And he's like, I haven't thought about that. I'm like, what do you mean you haven't thought about your periodic table element that you would name? I don't know. I think it would be fun. Anyways, back to what we're talking about, right? So chromium, that all happens. And then in copper category, that all happens going down where you're going to fill your entire 3D subshell and have only 1 electron in your 4s. It doesn't go into the Fs. Nope. You just need to know that for like essentially chromium and copper, but it happens for the entire row that it's in. Yes. Yeah. Does that help your question?
Yeah.
Okay. And then does that make sense in terms of naming it by the periodic table or by the noble gas or? Yes. Yep. Perfect. And then you would just put argon right before it, right? Argon and then 4s2, 3d3. And then that says, okay, you can go to argon first and now count this many electrons forward. Yep. Does that help? Okay. I think we'll call that good. If we feel, and if there's no more questions. Yeah. Does that help with stuff that we learned in class today? Okay. Yeah. I try to equate it to camp counselors or like walking a dog, right? And I'm like, I got it.